Welcome back, everyone. In this video, we will be discussing differences in differences, which is a very popular strategy to estimate causal effects from observational data that is longitudinal. Longitudinal meaning that the primary unit of interest, for example, a person, is observed over time. The application we will be considering today is measuring the impact of school funding on student achievement. Before we look at the specific data, let us first talk about the environment in which the data is observed. On the top left here, I have a state, and this state is made up of 4 different cities. Suppose that in 2012, this city, shaded in red here, received funding for all its schools. And this funding, for example, could be used to train teachers, provide computers and textbooks, and reduce class sizes. So we can imagine this is a great school funding package that will likely positively impact student achievement. I should also mention that the school funding was only provided to the city in 2012, but not in 2011. Now, the other 3 cities that are shaded in blue did not receive the school funding in either 2011 or 2012. So essentially, what this data environment gives us is 2 sources of treatment variation in the data that can help us learn the treatment effect. That is, the effect of the school funding on student achievement. The first source of variation is overtime variation, where we can examine how test scores change in the treated city in red in 2011 when they did not receive school funding to 2012 where the city did receive school funding. This type of comparison is known as the pre-post analysis, pre being before the treatment and post being during the treatment in this case. The second source of treatment variation comes from comparing achievement in control cities in blue in 2012 to the achievement in the treated city in red in 2012. This type of analysis is called the controlled treatment analysis, control being the blue cities that did not get the funding, and treatment being the red city which did get the funding in 2012. As we will very soon see, it turns out that differences in differences estimator actually uses both sources of variation to identify the treatment effect. Now that we have some understanding of the data environment, let us take a look at the example dataset. This is a school achievement dataset where we have 2 time periods, 2011 and 2012. We also have 2 types of cities, the treatment city which received school funding in 2012 and the remaining cities that did not receive the school funding are in the control group. Let's first plot the achievement data for the control cities. In the control cities, the school achievement increased from 65 points in 2011 to 70 points in 2012. This is a 5-point increase in school achievement over time in the control cities. Very similarly, we can also plot the school achievement over time for the treatment city. We can clearly see that the increase in school achievement over time in the treated city is higher than the control city. For the treatment city that received school funding in 2012, the test score goes up by 10 points, from 70 points in 2011 to 80 points in 2012. So this is the data we are working with, and what we essentially want to know is the impact of the school funding on student achievement. That is, we want to know how much of the 10-point increase in school achievement in the treated city over time is due to the school funding. To answer this question formally, let us consider the following regression model. Y equals beta 0 plus beta 1 times a treatment indicator, where this is a dummy variable where treatment equals 1 if the school is in the treated city, and 0 if the school is instead in one of the control cities. Then we have plus beta 2 times post 2011. This is also a dummy variable and is equal to 1 if the year is 2012 and 0 if the year is 2011. And finally, an interaction between the treatment indicator and the post 2011 dummy variable. Some of you may be wondering if something is missing from this regression model. There's indeed a component missing, which is the random error term. For this beginner level video on differences in differences, I'm going to ignore the epsilon for simplicity as it will simplify the math a bit and will not impact the final result. Now what we're going to show is that the primary parameter of interest in this regression model is beta 3. That is, beta 3 captures the treatment effect, the impact of the school funding on student achievement in this case. This will be true under a very important assumption which the differences in differences method relies on. This is called the common trends, or sometimes also the parallel trends assumption. The assumption says that if the treatment group did not receive the treatment, then the treatment group will follow the exact trend over time in their outcome as the control group. So for our example, suppose the treated city did not receive the school funding. then what do we expect their achievement to be in 2012? Well, under the common trend assumption, the treated cities' test scores would change by the same amount the control cities change over time. So then, we would expect the schools in the treated city to get an average score of 75 points had the treated city schools not received the funding in 2012. This prediction is indicated by the blue line on the plot here, and this is called the counterfactual. The counterfactual tells us what would occur in the treatment group in a world where they did not receive the treatment. Given the following three lines in this plot, I want everyone to think about what gap between the lines would represent the treatment effect. Feel free to pause the video at this stage and think about this for a few seconds. Well, I hope you did some pondering and hopefully concluded that the gap between the blue and red line is the treatment effect. This is because the red line in 2012 tells us what the school achievement would be if they received funding, and the blue line tells us the school achievement had they not received funding. So taking a simple difference results in the treatment effect. In our case, the impact of the funding on student test scores. For the remainder of this video, we're going to show that this treatment effect is actually beta 3, the coefficient corresponding to the interaction between the treatment indicator and the post-2011 dummy variable in this regression. We are going to start by doing a before-after analysis for the control group. The control cities have the treatment indicator equal to 0, and before the treatment means that post-2011 is equal to 0, and during the treatment period means that post-2011 is equal to 1. Okay, so if the treatment indicator equals 0, which means we are considering the schools in the control cities, then in 2011, where the post-2011 dummy variable equals 0, the average school achievement implied by the regression model is represented by beta 0. This is because if we plug in treat equals 0 and post-2011 equals 0 into the regression, then we are left with beta 0. Similarly, if we consider the control cities in 2012, the average school achievement is represented by beta 0 plus beta 2. To get this result, now we are plugging in treat equals 0 and post-2011 equals 1, so the interaction term is still 0. The before-after analysis in the control group tells us that the school achievement in the control cities changes by beta 2 over time. We get beta 2 by subtracting the model implied achievement in 2012 from the model implied achievement in 2011 as shown here. Since the control group did not receive any school funding, we can think about this change in test scores over time being mainly attributable to a trend. For example, if students are just working harder or getting smarter over time, let's say, then this would be captured by the trend in school achievement. In this case, we see that the school achievement increased by 5 points in the control cities, and we primarily attribute this increase due to a trend. Next, we can do a very similar before-after analysis for the treatment group where the treatment indicator equals 1. I encourage everyone to pause the video at this stage and think about the model implied school achievement for the treated city in 2011 and 2012. Well, hopefully you gave it some thought. In 2011, we have post-2011 equals 0. So when we plug in treat equals 0 and post-2011 equals 0, the model implied school achievement will be beta 0 plus beta 1. Now when we plug in treat equals 1 and post-2011 equals 1, none of the terms in the regression are 0, so we get the average school achievement in the treated city in 2012 is beta 0 plus beta 1 plus beta 2, and finally the interaction term beta 3. Subtracting the model implied school achievement in 2012 from 2011 in the treated city results in beta 2 plus beta 3. That is, the change in school achievement in the treated city over time is beta 2 plus beta 3 as shown in the figure. Since this treated city received school funding in 2012, we can attribute some of this change to the treatment effect and the remaining change due to the time trend in school achievement. In our example, school test scores in the treated city increased by 10 points over time, and we believe that some of these 10 points is due to the school funding and some of it is due to a trend in school achievement. Using what we have so far, we would like to isolate the treatment effect, that is the impact of school funding on achievement for the treated city. To do this, we are going to revisit the assumption we made earlier, the common trends assumption. According to the common trends assumption, the school achievement trends in both the control and treatment cities will be the same in absence of the treatment. Since the two trends are the same, we can take the difference in the before-after analysis across the treatment and control group to cover the treatment effect. Now you can see why this estimator is called the difference in difference estimator, because it involves this double differencing idea. In our example, the difference in difference estimate is 5 points. This estimate says that the school achievement in the treated city increased by 5 points over time relative to the control cities that did not receive any school funding. Something I should mention here is that there are two ways to compute the difference in difference estimate. So far, we have used one of them by measuring how much the change in school achievement over time differs across the control and cities and the treated city. We can also equivalently consider how the difference in achievement across the control and treatment group changed from 2011 to 2012. In our case, the 2011 difference in school achievement across the treatment and control city is 5 points, and the difference increases to 10 points in the treatment period in 2012. So the difference in difference estimate is still 5 points. We can also derive this way of double differencing from the graph as well. The math changes a bit, but we get the exact same final result. In 2011, the difference in school achievement across the treatment city and the control cities is represented by beta 1. And in 2012, the difference in school achievement across the treatment and control cities is represented by beta 1 plus beta 3. Now we can take the difference of these two first differences as before and get the treatment effect of beta 3. Feel free to pause the video and double check the math for yourself. To summarize, differences in differences is a method that can be used in longitudinal data where the unit of interest is observed over time to estimate the causal impacts of the treatment on the treated units. The data environment required to apply differences in differences is the pre, post, and control treatment environment. The control group never receives treatment, but the treatment group eventually receives treatment in the treatment period. For our example, we took advantage of this pre, post, and control treatment environment across cities and used it to find that the school funding increased test scores in the treated cities by 5 points on average.